reproduce the equations here, and this is sort of amusing. When you add them, this term exactly cancels the difficult part of the magnetization. And actually, as a side remark, you can also derive this, which Chen Niu did 5 years before, using a purely Berry phase calculation. Nothing to do with thermal gradient, just a purely simple electron gas problem with Berry phase. And they obtained the orbital magnetization has exactly the form that Murakami derived from the Kubo approach. Okay, but if you add them, the difficult part cancels out, leaving behind a rather simple form, which is exactly what we had obtained, or they had obtained, using the semi-classical equation. So it all works out. Right? So I find this theory to be convincing because you don't have any wiggle room, so to speak. Right? Okay, anyway. So the two materials are the pyrochlore, terbium titanate. So this, to answer the previous question, this has a high temperature Curie-Weiss susceptibility that predicts a Curie-Weiss temperature of 19 Kelvin. So it should have ordered, plus or minus a factor of 2 at this temperature. But folks have cooled it down to 50 millikelvin and nothing happens. So it's in zero field. Once you apply a field, you spoil the frustration and it orders. So this is sort of a leading candidate. And some people call this the quantum spin ice. Anyways, there's been 20 years of neutron experiments, and people get better and better neutron data, but it still remains an open problem. Absolutely no transport measurements on it. Well, a few transport, but not much. So we thought we would search for the effect in this material. This, by contrast, is a ordered magnet, but it has Kagome planes based on copper, and it orders it around Kelvin. So okay, I don't need to say more about this. So for a Lorentz force with a charged particle, this is the familiar cyclotron motion that leads to the Hall effect. So the question is, if you had a wave packet of spin excitations, can a magnetic field bend its path to give you a Hall effect? And the original Nagaosa-Lee model was based on this chirality of the Kagome lattice. Yeah.
You said that you can have spin ice in the
quantum spin ice, yeah.
Yes. How is this related or different from spin glass?
Completely different. Spin glass is the following. You take copper, pure copper, and you stick in a lot of manganese atoms. This is the canonical spin glass. Okay, so imagine copper with a dense collection of manganese. So manganese has a local moment, right? However, the manganese separation is completely random, right? So it has a Gaussian distribution, right? Now, manganese in copper does have an exchange, and that comes from, one local moment induces a 2kF RKKY Rudiment-Cattell oscillation, right? But if the separations are random, this second spin will either have the itinerant electron spin pointing up or down, depending on how far they are. So the exchange that results is completely random. Again, a Gaussian distribution. This thing never orders, but it goes through a spin glass transition, which is a 50-year-old problem. There's no sharp order parameter. Well, there's something called the Anderson, forget the other guy's name. Edwards. Thanks. If you write a paper with Anderson, there's a big danger that your name will be forgotten. So this is completely different physics. There's no long-range order, but it does order. It orders in a crazy way that's not very well. Here, it's completely different, right? So I'll talk about spin ice, I think in the next slide, right here. Yeah, here we go.
And in this pyrochlore, are you sure that we don't have any spin glass? Why can we?
So this is a yeah. So yeah. So I would have said no, but then last week Seamus Davis told me that he has evidence to show that this monopole physics may not be right, and it actually has a spin glass type of behavior. Yeah. So this is at the forefront of research, and I don't know how it's going to play out. Okay. So what is the spin ice system, right? So here you have in each tetrahedron, the spins can either be in or out, and that reminds you of the water ice problem, right? In water ice, the hydrogen has two positions to sit, and this gives rise to extensive entropy at very low temperatures. So spin in the spin ice problem, Ramirez first showed that indeed the entropy at very low temperatures is extensive. It's huge. It scales like a volume. And in fact, it's in rather good agreement with Pauling's formula. The quantum spin ice has no such order, and it, as I mentioned, it remains disordered down to very low temperatures. So there are two of them that we studied. I will just tell you about terbium. Ytterbium behaves more or less the same way. Actually, ytterbium is an even better example than terbium, but that came a lot later. So here's the thermal conductivity. When you cool down, I'm dividing by T so that this gets amplified a little bit, right? So I'm removing an extraneous factor of T that appears in all thermal conductivity expressions. So it reaches a peak, and then it comes down and it becomes a very poor thermal conductor below 5 Kelvin. So I'm blowing up the region below 10 Kelvin, and you can see that the phononic decrease gets interrupted, shorted up, so to speak, by an excess that we would like to ascribe to spin excitation. But now this is very weird, right? Because there's no ordered phase, and it's not clear. If you ask me, what are these excitations? Well, I don't know, because there are no magnons, there are no spin waves, right? Definitely no spin waves because it's not ordered. And yet there's a lot of spin excitations here, and this is where we're going to search for the thermal Hall effect. So before we do that, we can measure the kappa XX, the thermal conductivity in a magnetic field. And when you get to low temperatures, at high temperatures it's flat. The magnetic field has no effect on the thermal conductivity. But below 10 Kelvin or so, you start to see changes. And at very low temperatures, it has a very poor thermal conductivity, but rises immediately at about 2 Tesla. And this was actually detected by neutron scattering, that if you look at neutron diffraction, the Bragg plane, the Bragg volume is completely uniform and featureless in zero field. But when you apply a magnetic field, the diffraction pattern condenses into a bright peak, which indicates field-induced ordering. And we think we're seeing the same thing in the thermal current. So this would appear to signal the existence of spin waves in this ordered phase that's field-induced. Right? Yeah, I think I said all these here. Okay. So here are the initial experimental checks. Max, the student doing this, Hirschberger, Max saw a very large thermal Hall effect. And this is always nervous, right? Because you're looking for it and you find a big signal. So you want to make sure that it's real, that you're not making a fool of yourself when you publish it. So one of the tests is to reverse the heat current. And so if it's a thermal Hall effect, when you change the heat current direction, it should reverse in sign, right? And it does. So this is actually easier said than done, because unlike an electrical measurement where you simply go up to your current source and flip the sign, there's no way to flip the sign of a thermal current, right? You have to go in there and laboriously change the heater connections, and then so you initially heat this end, right? So the heat current flows to your right, and then you warm the system up, remove this gold wire, attach this one here, and then reverse the current, hopefully without changing the sample. And remarkably, you see the Hall signal reverses sign. So this is really a Hall signal. It changes sign with the direction of the current, as well as the field. Field you can change in situ, obviously. Right? So that passed the test. Moreover, it scales linearly with the heater power, right? So going from 90 to 250 microwatts, you see the same kappa XY. So you're measuring something real rather than a spurious effect. And you'll notice I've colored this orange. The sample is sort of pinkish orange. So it's completely transparent. So this is very strange, right? You have an insulating material that has no free electrons, and yet the magnetic field can deflect the neutral current. And the sign is completely unknown. What determines the sign, right? It presumably is how the buried curvature gets aligned up or down. You can also compare this with a analogous pyrochlore that has no magnetic moment. So this is yttrium titanate, which Kava's group was kind enough to grow for us. And you find that it has no such signal at all. And actually, it's worse than what this plot says, because here we are applying a very feeble power, a very large power, sorry. So this is something like a factor of 40 compared to here, right? And yet, it is, there's really no power at all. This tiny, if you have good eyes, you notice that this end is a little bit higher than this end, right? And that comes from the substrate. Actually, the substrate itself, which initially we had used copper, starts to influence the Hall effect. But anyway, that's neglecting this tiny correction. This signal is down by a factor of 40 times whatever this is, 8. Okay, so this summarizes the thing. So this is an intrinsic signal. It's an insulator that has spin excitations. They carry neutral current, and you can make their Hall current go to the left or to the right by either changing the current direction or the field direction. So it's a true Hall effect. So knowing that, then Max measured this in great detail. Here are raw traces of kappa XY, again divided by T. And at very high temperatures, it's still there. So it's not an abrupt appearance at some order. It's always there when you have spin excitations. They're identical. All pyrochlores have the same lattice structure.
So what symmetry are you breaking in your
one has a local moment, the other one doesn't.
I see. And which atom is giving rise to that?
So this is the terbium or terbium. Yeah, here we're talking about terbium titanate. So terbium is a large one.
So you're breaking the time reversals.
We're not playing a field. So we're having all these local moments, and then they order in some crazy way, right? There's a huge exchange energy, but still they do not order. They don't form a spin ice, and so whereas the yttrium, we call it the vegetable, the yttrium doesn't have a local moment at all, so there's nothing to speak of. But they all have the same identical crystal structure. So it reaches a maximum kappa XY at about 15 Kelvin. Then when you go to lower temperatures, it starts to come down again. And at the lowest temperature, here's 1 Kelvin, it has some action around 2 Tesla that remains to be sorted out. Okay, so one way to analyze this is to look at the thermal Hall angle, right? Take the ratio of the Hall current to the longitudinal current. So that's a measure of how much deflection you get in the magnetic field. And it's fairly large. Although it looks smallish, right, 5 milliradians, it's still quite large in these kinds of measurements. So you see that as at the lowest temperature, 0.8, it increases linearly and then starts to come down. By the time field ordering happens, remember I told you at 2 Tesla, there's some kind of magnetic ordering that occurs when the diffraction spots condense. Interestingly, it wipes out the thermal Hall effect. So this is a property intrinsic to the weak field entangled state that we identify with the spin liquid. Here's one other way to show it. We plot this slope, initial slope that's indicated by this ratio, versus temperature, and put it on log scale. And you see that it increases very rapidly below about 50 Kelvin, and then in this interesting phase, it saturates. So we detect a phase at very low temperatures that has a lot of spin excitation, and they have this interesting novel property that they have a thermal Hall effect. And it's a very fragile excitation. When the system orders in a strong field at 2 Tesla, it goes away. Right? So in fact, you would have thought that, well, when it orders, you should have a lot of spin waves, right? But the spin waves do not add to the thermal Hall effect. In fact, they basically remove this interesting excitation. So one way to show this is in the phase diagram, field versus temperature. And so the experiment is done by holding the temperature and sweeping the field, right? So making cuts like that. And you can see that this interesting phase gets progressively narrower as the field-induced effect kicks in. So it's again, yeah, it looks like it remains there at 0 Kelvin. And this is cuts. These curves are cuts at fixed field going vertically. So you see that there's this very large Hall angle response in the sample. Okay, this is currently a very interesting topic, and there's a lot of theory regarding what the nature of this spin liquid is. A lot of the work comes from the group of Leon Balance. I won't go through all this because it's not clear that how you would detect these interesting excitations. Yeah.
In the last slide, the phase diagram. What are the 2 phases? The black one. Which one is being iced?
There's no spin ice in here, we think. So this boundary, somewhere here, you go through a metamagnetic transition. So the field, the applied field, is forcing all the local moments to line up, and then they order. Because in the neutron diffraction, they see this very broad diffuse background condensed into bright Bragg spots, magnetic Bragg spots. So over here, it's probably ordered magnetically. And my comment was that you get magnons here, probably, right? Because you saw that the kappa XX made an abrupt jump, right? Let me remind you. Here, right? It makes an abrupt jump. So it's there's a lot of heat carried by these new spin excitations, but the thermal Hall effect goes away. Right. So the thermal Hall effect just goes away.
All right. So what is that black phase then?
That's the interesting state that presumably is part of the spin liquid scenario.
I see.
Okay, so the part 2 of the talk, let's see. Am I out of time? I think I am. What time am I supposed to start?
I think you have 15.
15 more minutes. Yeah, if I run out of time, I'll continue in the second talk, part of this, because the second talk is even shorter. Okay, so it'll be nice to actually do this in another system, right? So yeah.
Could you talk a little bit about the phase?
This one here? Oh, this one here.
Yeah.
Well, I cut it short because a lot of it I don't understand. So there are this, this is the